Well, thank you very much, and I also want to thank the organizers of the conference for giving me the opportunity to speak to you today about the latest work at Rice University on ultracold neutral plasmas. These are experiments in which we use the tools of atomic physics to access regimes of neutral plasmas and study fundamental phenomenon which would not be accessible in other ways. So today I'll start with giving a little bit of a background on all that you really need to know about ultracold plasmas, and then I'll talk about two of our more recent experiments. The first is laser cooling of ions in a neutral plasma, and then the magnetic confinement of these plasmas as well. And if I have a little bit of time at the end, hopefully I'll be able to talk about some future directions. So we create our ultracold neutral plasmas by photoionizing a laser-cooled gas just above or just near the ionization threshold. In my laboratory, we work with strontium in a magneto-optical trap. So we have about 1 billion strontium atoms laser-cooled to about 1 millikelvin with a peak density of around 10 to the 10 per cubic centimeters. And then we ionize the gas, as I said, just above the ionization threshold with a 10 nanosecond pulsed dye laser. And we can adjust the ionization threshold anywhere up to 50% or so. So we get a few 100 million ions, and the size and the shape of the plasma follows the density distribution of the original laser-cooled gas, so typically about millimeter in size. And our peak density then is a few times 10 to the 9 per cubic centimeter. And the electron temperature is set by the detuning of the laser above the ionization threshold. So we can tune that from about 1 to 1,000 Kelvin as desired. And the ions, which will be of more interest in what I talk about today, they, at least initially, stay at the laser cooling temperatures. They take very little of an impulse kick from this ionization process. So they start in the millikelvin temperature regime. So there are a handful of experimental and theoretical groups around the world that work with these systems. And their symbols are shown here. And there are some variations on the recipe that I have shown to you, such as starting with especially molecules in a molecular beam. You can ionize them to form an ultracold plasma. And also at Hamburg, there are recent results using an ultra-fast laser system, which is important for studying the electron dynamics in these plasmas. But I'll be focusing on the ions and with strontium out of a magneto-optical trap. So this diagram of the phase-space density of ultracold, or phase-space parameter regime of neutral plasmas shows why these ultracold plasmas are interesting. So here's temperature versus density. Cold for a plasma physicist is typically around 1,000 degrees Kelvin, like a candle flame or a near-Earth space plasma. And this is the minimum temperature required to maintain ionization through collisions. But our ultracold plasmas are down access sort of the 1 Kelvin regime or so orders of magnitude colder than traditional plasmas, and they cross into this regime of what's called strongly coupled plasmas, where it's typically felt or thought that it's too cool and dense for plasmas to exist. So this regime is characterized by the Coulomb coupling parameter being greater than 1, and this parameter is the ratio of the interaction energy, the Coulomb energy between nearest neighbors, where A is the average interparticle spacing, to the typical thermal energy or kinetic energy, kBT. So this strong coupling is the typical same kind of parameter that describes strongly interacting systems in condensed matter or high energy physics. It's the same kind of concept. And in this community, we're actually familiar with the effects of strong Coulomb coupling from laser-cooled pure ion plasmas, typically trapped in magnetic traps or RF traps. Here's a picture from the NIST ion trapping group. And strong coupling leads to the establishment of spatial correlations. Initially, when gamma is just greater than 1, you get liquid-like short-range correlations, but for larger gamma, you can actually get Wigner crystallization in solids forming. So here are non-neutral ion plasmas. Also, you can see the same kind of phenomenon in dust particles inserted into plasmas that charge up to very, very high charge states that also give strong interactions. In natural settings, you can get strong coupling in white dwarf stars or the interior of a gas giant planet. You can also get strongly coupled situations in experiments with intense lasers, such as inertial confinement fusion experiments or other systems studying high energy density systems. And so what's really helpful is to have these laboratory-based systems in order to study the complex physics that arises when the interactions get strong and it's hard to use traditional theory. So there are lots of different reasons that the ultracold plasmas are interesting, even some applications, but definitely one of them is this ability to simulate and benchmark theories for strongly coupled plasma systems. And we've been doing this for quite a while in my laboratory, studying various transport phenomena. And now, as I'll talk about later in the talk, we've added magnetic fields into the system, which adds new phenomenon, and also magnetic fields can also be present in some of these dense astrophysical systems as well. I won't get to talk about it today, but the way we create our plasmas gives us fantastic control over the density distribution of the system. For example, just by sculpting the laser intensity that ionizes the gas. So we can create flows or other interesting density structures that can actually lead to very interesting and complex motions of the plasma fluids. And so we've used this to also simulate and benchmark theory in various hydrodynamic and kinetic regimes that has been of interest to space plasmas, even modeling plasmas on the surface of the sun. There actually have been some directions trying to develop ultracold plasmas as sources for bright charged particle beams for ion and electron microscopes. Having very cold collections of localized charged particles can be helpful for that. So that's another direction that's been exciting to see. But mostly what I like to do is to use these tools to stretch the boundary of plasma physics and see how systems behave in these unusual regimes. And laser cooling certainly helps us to do that, to stretch towards colder temperatures. So this diagram of different time scales gives you a very brief introduction of what happens to the ultracold neutral plasmas after we create it at t = 0. On a very short time scale of about 10 nanoseconds, the electrons equilibrate locally and even globally across the plasma. They however, while the electrons would like to run away because they take away most of the energy from the ionization, they're attracted to the space charge of the more massive ions that really are not moving at all on this time scale. So the ions create a Coulomb well that holds the electrons in place. On a little bit longer time scale of about a microsecond, the ions equilibrate. And I'll talk quite a bit about that in another slide or two. And then on a longer time scale of 5 to 10 or 100 microseconds, then you get bulk motion of the plasma. Really, typically, a hydrodynamic description will explain what's happening there. And the time scale for this is set by the ratio of the size of the plasma to a typical velocity that's given by the kinetic energy of the electrons or the ions divided by the ion mass. And this time scale is typically 10 to 20 or 30 microseconds. The experiments I'll talk about today cover these two regimes, and that's because that's where the strong coupling physics comes into play, but also we have powerful diagnostics to look at the ions. What we use is a laser-induced fluorescence, and that's really the only reason that I use strontium. Really, any laser-coolable atom would do, but using an alkaline earth or alkaline earth-like atom means that after you ionize it, you still have an easily accessible optical transition to scatter photons off your ions. So we drive the 422 nanometer transition in the strontium ion to image the plasmas. So we typically will construct our laser-induced fluorescence beam in a sheet of light that passes through the center of the plasma, so we don't have to do any density averaging. And we image the fluorescence perpendicular to that laser sheet onto an intensified CCD camera, and that gives us the density distribution of the plasma. And we can do this in a time-resolved fashion if we want to, with sort of 50 nanosecond resolution time. But this laser-induced fluorescence process it's Doppler sensitive, and the velocities of the ions are large enough that the Doppler shifts are important. So as we scan the frequency of this laser-induced fluorescence beam, we can map out the laser-induced fluorescence and essentially get a velocity map of the ions in the plasma along the directions of the ion. So in this way, we can measure the temperature of the ions if it's thermal, or as you can see, lots of times there's structure on the velocity distribution that could tell us a lot about the motion of the particles in the plasma. So here is a sample of the ion temperature as a function of time after creation of the plasma here. And so as I advertised, initially right after plasma creation, the ions are very, very cold, as cold as our diagnostic can measure. But when the plasma is created, it's essentially turning on this very strong interaction, the Coulomb interaction. The atoms are essentially non-interacting, but when the strong Coulomb interaction is turned on, the system heats up very rapidly to typically something on the order of a Kelvin. And what's happening here is that the ions, when they're created, they have very little kinetic energy, but they have a very large amount of potential energy because they're created in random positions that are inherited from the non-interacting atoms. And on this time scale of about a half a microsecond, the system is rolling down a potential energy surface as spatial correlations are developing, and this potential energy is being released into kinetic energy, and this energy scale is set by the density of the particles, and it's essentially the typical electrical interaction energy between nearest neighbors. So after the system equilibrates, then we can measure or read out the ion Coulomb coupling parameter, and typically these systems will equilibrate at temperatures, at Coulomb coupling parameters of around 2 or so. And this is actually, no matter how you tune the system, lower density or higher density, you always end up with Coulomb coupling parameters around 2, because this essentially is an equipartition of energy during this equilibration process. Now, you might notice that there are interesting kinetic energy oscillations that happen during this equilibration. This is one of the many things we see that are signatures of how systems that are strongly coupled behave differently than weakly coupled systems behave. But I won't have time to talk about this today. The important thing, though, is that the system heats up to this 1 Kelvin, Coulomb coupling on the order of 2 or so, really no matter how we vary the creation process. And so here I've shown various molecular dynamic simulations of plasmas at various Coulomb coupling parameters. For low Coulomb coupling, the system behaves gas-like, and the coupling parameters we access, there are short-range correlations developed that are changing the transport properties, a breakdown of traditional theory. So molecular dynamics is really the only way one can use to get at the properties of these systems. And this is about all we can get to with the traditional ways of creating our plasmas. But if we can go colder, then we can get to a stronger liquid-like behavior. There's different phenomena like caging of the particles, and eventually even crystallization of the particles. So a lot of interesting physics if we could go colder. So that's what has driven this field to try to find techniques to somehow increase the Coulomb coupling parameter or cool the system further after it's created. And so that drove us to look into the possibility of laser cooling the ions in the neutral plasma after we created them. Now, with this audience, I don't have to talk about how powerful laser cooling is, and every time it's been applied to a new physical system, it's opened up new applications and new regimes of nature to explore. And so, obviously, atoms and ions are well established, and now we're seeing great progress in other systems with molecules, even solids or mesoscopic quantum oscillators. And so the results that we got just a couple of years ago were the first applications to laser cooling ions in the neutral plasma, so with the electrons still around as a neutralizing background of the system. So the experiment from a laser cooling perspective is actually quite straightforward in hindsight. We set up a simple 1D optical molasses on the principal doublet S1/2 to doublet P3/2 transition at 408 nanometers. So we pass circularly polarized light through the system, reverse the polarization, and reflect it back upon itself. And this creates the standard velocity damping force in one dimension. There are a few complications. There are strong leaks from this cooling transition with a branching ratio of about 1 in 15. So we really need to have repump lasers on in order to scatter enough photons to cool the system appreciably. So there are a few challenges, or at least differences, in laser cooling in a neutral plasma compared to laser cooling even trapped ions, never mind weakly interacting atoms. The first is that we have to worry about a very rapid expansion of the neutral plasma, and I'll say a few more words about each of these. We also have a very collisional system. So the systems are colliding, the velocities are being thermalized on a time scale much faster than the laser cooling time scale. And then with all the lasers that we have to apply, especially the repumpers, there are a lot of dark states or velocity-dependent EIT resonances that you might have to worry about that you might think would greatly reduce the cooling efficiency if you pump ions into some of these dark states. So I'll say a word or two about the expansion of the plasma. I should have mentioned that for these laser cooling experiments, we turn off the magnetic field of the MOT, so this is all in a field-free situation. So the expansion of the plasma is essentially driven by the pressure of the electron gas. The electrons are held in by the charge of the ions, but they really want to run away, so you really could think of the ions as a box that's holding in this ideal gas of electrons that's exerting a pressure. And if you do a hydrodynamic description of the system, you can show that the force, a force field that accelerates really just the ion fluid, the electrons come along for a ride, that force is directed along the gradient of the density, and it's proportional to the electron temperature, which is where the force comes from. And so this creates a radially directed velocity field that increases in time and increases in space away from the origin of the system. And that time scale for these velocities to build up is that same time scale that I introduced in the beginning of the talk, and it's typically around 30 or so microseconds if you start with a nice big plasma, which is a good starting condition if you want to laser cool, because you want to make this a very long time in order to have time to laser cool. Now, it's important to get a sense of the scale of this expansion velocity. So on this order of a few tens of microseconds, the average expansion velocity for the conditions we work with is going to get up to be on the order of many tens of meters per second. And so you would want to compare this to the capture velocity of our simple laser cooling setup. So it's significantly larger than the capture velocity of 10 meters per second for our laser cooling transition. And it's also much more than the thermal velocity of the ions of about 10 meters per second. And also this time scale of the 30 microseconds or so is on the order of the time scale you estimate for laser cooling, just looking at the energy damping time for simple optical molasses. So all this, you put this all together, it means that really these ions out at the edge that are rapidly accelerating away, you're not going to have time to laser cool them. So under this scheme, you'd only expect ions in the center of the plasma to be able to be effectively cooled. So we'll see that show up as well. Now, the rapid collisions are also important. At the same time scale at which the system equilibrates, that's the time scale for the randomization of the ion velocities. So this fast randomization means if I want to do laser cooling, I have to cool all the velocity classes at once. I'm not going to see a signature in cooling just one velocity class, for example. Now, there's some advantages of the collisions, though. It means that just a single one-dimensional molasses should be able to cool all 3 degrees of freedom. And more importantly, the collisions wash out these velocity selective dark resonances. So it turns out that that's not a limitation for the laser cooling. However, we didn't know all these things when we started, so we developed a simulation that combined the molecular dynamics and the plasma physics with a quantum trajectories calculation of the laser cooling process ion by ion. And we published this just a couple of years ago. This has turned out to be a very powerful tool that helped us to choose the right parameter space in order to get laser cooling to work in the plasmas. In the end, what you really just need is a lot of laser power, and then it works quite well. So here are the first results. So here is temperature and a slice along the center of the plasma for 3 different configurations of the laser cooling. The green is no laser cooling, the red is red detuned, and the blue is blue detuned by about 1 line width of the transition. So after 5 microseconds, there's no sign of laser cooling. You see a little bit of variation in temperature. This is just from variation in the density of the sample. So denser regions heat up a little bit more than the less dense regions, so that gives us variation in temperature. But if we apply those laser cooling fields for longer, by 60 microseconds, we can see the clear signature in the center of cooling the system from the several hundred millikelvin to by at least 100 millikelvin in this case. And the blue detune actually efficiently heats the plasma as well, as one might expect. And if we go for about 130 microseconds or so, we cool the plasmas down to about 50 millikelvin for the cooling configuration. Now this is actually about as cold as we can measure because now the Doppler width of our transition is so broad we can't measure it any colder. So it's certainly possible we could be cooling it further. And the heating can heat it up significantly as well. This overall temperature drop is just adiabatic cooling as the plasma expands. And as you can see, it's in the central region is really where you see the cooling. So it's showing you how this expansion really is playing a big role in how well the laser cooling works. So I started this all off by talking about Coulomb coupling. So I look at the center part of the plasma where we cool it most efficiently. The coupling parameter equilibrated to around 2.5, as I said earlier. But after laser cooling, we can get it up above 10 to 11, or even 12 is the most we've gotten to. And that actually gets it into the regime of things like white dwarf stars. So that's nice that we can access this regime where if we study transport properties or other physics, we can see more variation from traditional theory and touch base with these other systems as well. And it's nice that the heating actually can decrease the Coulomb coupling parameter, so we get a large range of now order of magnitude for using this as a tool to access a wide range of parameters of the system. Now, something that I hadn't really expected when we set out these experiments is that the laser forces are actually enough to affect the expansion of the plasma as well. And one of the reasons why I didn't quite expect this is because the forces that we talk about here for the expansion of the plasma are quite strong. And that's certainly the case in the early time of the plasma. So here is expansion of the plasma without the laser cooling fields. Again, no magnetic field as well. And you see the plasma is expanding into the surrounding vacuum on this 100 microsecond time scale. But when the laser cooling lasers are applied, and they're applied along this direction, for the first 30 microseconds or so, there's no effect on the expansion. That's because this force is just too strong. The electron temperature is still relatively high. The gradients of the density are large. But all those effects are changing with time. So by the 50 or 60 microseconds, this force is greatly reduced. And then your laser cooling forces can really be significant. So we see that compared to the no lasers, you really are retarding the expansion of the plasma. And when you put the blue detuning for the heating lasers on, you can literally tear the plasma apart as well. So what's really exciting to me about this is showing that the laser cooling forces are really in the range where you can start to think about them as confining the plasma, which would really be an exciting result as well, to create a new way to confine a neutral plasma. And it's reasonable to expect that if you combine magnetic forces with the laser forces, or like a magneto-optical trap, you could also get very interesting trapping dynamics. So that motivated us to start to put magnetic fields onto the plasma and see if we could bring that into the game as well. Now, magnetic fields are very important in plasma physics in a whole range of areas, but in particular in the area of strongly coupled plasmas, they really add a lot of complications and rich physics. And a lot of the earliest experiments with the strongly coupled plasmas, such as the ions, pure ion plasmas and magnetic traps, they've studied the dynamics of these strongly coupled systems in very strong magnetic fields. And this is also similar physics to what was used to create overlapping positive and negative charged clouds for the production of antihydrogen as well. So this trapping of neutral plasmas in magnetic fields is interesting in many different areas. From a pure plasma standpoint, and especially in the strongly coupled areas such as high energy density plasmas, modeling the interior of neutron stars, well, the exterior of neutron stars, the interior white dwarf stars, the magnetic fields are important to those regimes. So there's really a desire to try to create laboratory accessible strongly coupled plasmas that are also magnetized. And a recent article mapped out sort of all the different types of regimes one could access as the length scale of the gyro radius changes from the collision mean free path to the screening length of a plasma to the average interparticle spacing. You get different regimes of the collisional and transport properties. So this is the kind of physics we'd like to access, and ultracold plasmas actually can explore quite a large range of this, at least in principle. And there has been very little work previous to ours on ultracold plasmas that are magnetized, but there was an important work in 2008 putting a plasma in a very, very large magnetic field and showing how the expansion was retarded. In our system, we were able to take advantage of the standard magnetic field that you get for a magneto-optical trap. So just a quadrupole field. Turns out that makes a very nice trap called in the plasma community a biconic cusp or quadrupole trap, where you have some stable trapping here at the center region where the field is very, very low. And the ions are only very weakly magnetized with gyro radius on the order of a millimeter, so on the scale of the size of the system. Whereas the electrons are very, very strongly magnetized with gyro radius on the order of a micron or so. And we published the results that showed the first magnetic trapping of an ultracold neutral plasma a little over a year ago. So I won't go through this in any detail, but this trap actually has a long history and has been studied in the plasma community for quite some time. So here's showing the trapping effect. Well, first, this is no trapping effect. So it's just the expansion without a field over a couple hundred microseconds. The plasma expands into vacuum. And here's the velocity map And these straight lines basically show that you've got a radially directed expansion velocity. Remember, we're only measuring velocity along one direction. And when we put on the biconic cusp field, initially there's no change in the expansion because the plasma is too energetic, the field is too small, so it has no effect. But as the plasma expands into the regions of larger field, you can see the plasma starts to conform to the shape of the field and eventually actually shows stable trapping. So really what's driving this is the electrons are getting pinned to the field lines and the ions are staying attracted to the electrons by electrostatic forces. The velocity, there's lots of great stuff happening here as well. We can map out the velocity. What's really interesting to see is you can see some variations in color here. I don't want to go too much into the details, but the patterns in color here essentially show that as the ions are traveling outwards, their velocity is actually reversing as they go and escape out these loss gaps of the plasma. But with time, the plasma is permanently trapped, and the effect that's causing this permanent trapping is a magnetic mirroring effect, which comes from the conservation of the magnetic moment of the electrons cycling around these field lines. For the kinetic energy of that motion increases, and it steals energy from the longitudinal motion and eventually makes the particle turn around. So this gives us stable trapping. And we've shown trapping time scales on the order of half a millisecond or so, which is actually quite respectable for neutral plasma trapping. So far, these systems here are the regimes where the electrons are and the ions go. You could imagine if we ramped up the magnetic fields, perhaps put in a large superconducting magnet around this, then we could get into this more interesting regimes as well. So I think I'm out of time, so I'll skip over the spin polarization of our plasma. It turns out that when we create these plasmas in the magnetic field, we get a spin polarized plasma for free. So if you have any questions for the question period, I'd be happy to talk about that. So there's a lot of future directions for us to go in. We'd like to characterize the magnetic trapping in stronger field gradients, understand the loss, and there's a lot of work to do in the modeling of these systems. The interplay of hydrodynamic and kinetic effects are very complex and can stretch our ability to describe these plasma systems. And our overarching interest is to be able to use these systems to study transport in the magnetized, strongly coupled regime. And hopefully we can combine the lasers with the magnetic fields for to try to get longer confinement times and perhaps colder and more strongly coupled systems. And eventually explore what are the limits to magnetic confinement and laser cooling. So I'll leave these conclusions up here. Special thanks to Tom Langen, who's in the audience. It was his thesis work on the laser cooling, and Grant Gorman, his thesis work was the magnetic trapping, and Mackenzie Warrens and Nina Inman are the current graduate students on the experiment. So thank you very much for your attention.
Thanks, Tom. The session is open to questions or comments. Spiel.
So you got trapping that lasted half a millisecond. What limits that? What are the processes that keep it from?
So these traps are lossy. The magnetic mirroring, you can imagine that this trapping is proportional to the transverse velocity of the ions and electrons. So if an electron is moving straight out along the field line, there's no trapping force and it can go right out. So these traps have loss cones. And so charged particles that initially have velocities along those, they get out, and then collisions will eventually mix and give you the whole sample eventually will go away.
Is there anything that's the equivalent of the kind of Majorana transitions that lead to losses in the more conventional atom traps?
Yeah, in principle, yes. I don't think those are going to be the dominant loss in this process in these systems, because you also have the collisions are so powerful, knocking them off field lines. So I think the transport, knocking these magnetic moments off field lines through collisions, I think will be more dominant over the Majorana type processes.
Yeah.
I'm very curious about your spin polarization results. We were working on spin polarization in the regime of wake field acceleration, and we used the phenomenon that basically strong field ionization is able to, in circular polarized lights, is able to produce spin polarized electrons. And we use this mechanism to inject electrons in the wake field. So I was wondering because you said that you could expand on this. Thank you.
Yep. So I think we get the spin polarization through a simpler process than that. Turns out that we start when we form our plasmas by photoionizing atoms out of a metastable, magnetically trappable state, helps us build up atoms. So in the atoms here they're two valence electrons, remember. Both of them, they're stretched, so both of them are aligned along the magnetic field. And when the laser pulse comes in and ionizes, it rips off one electron, and that takes away any angular momentum in the photon, but the electron left behind is still going to be pinned to that field line, at least to a good extent. This is actually a pretty well-known process in the formation of spin-polarized targets with spin-polarized helium atom, for example, and ionize it. I think in the particle physics community, this is or nuclear physics community, this is well known. So that's how we get them, and by using polarized light for our laser-induced fluorescence, we can see the patterns of the fluorescence that show us that we have a high degree of spin polarization in these systems, and it's preserved during the plasma dynamics.
Could you create a second mod on another axis and alternate between the two mods and eventually trap those atoms that would escape along one line?
I hadn't thought about setting up a second MOT, that magnetic field. I had to think about whether I could do the magnetic field, two different quadrupole fields to do that. But certainly it seems reasonable to apply lasers that try to plug these loss processes. That I think is sort of the low-hanging fruit, which could hopefully give them a much longer trapping time and much longer for the laser cooling to work to hopefully make that much more effective.
You've described the motion of these electrons and ions classically. Would you ever reach the domain where their quantum mechanical motion would become important?
I think it would be hard to envision in this system. The electrons if we get them very cold, it turns on recombination processes that will then destroy the plasma. I think probably the best opportunity to see quantum effects would actually be to go to ultra-fast ionization, which is what experiments in Hamburg have done recently, where you could hope if you started with a quantum regenerate sample, you could perhaps see the change of statistics going from Bose-Einstein condensate to a Fermi gas, for example, affecting the phase space density and the ionization, but have to be so quick before the particles start to accelerate and explore more phase space. So in my experiment, I think it would be very hard.
I'm here, yes. There's some really nice experiments recently, of course, with people trapping atoms in lattices and things like that, so they could presumably prepare the atoms further apart than you do. Can you see some advantages or some interesting directions that could be taken?
Yeah, I think there's lots of really exciting things you could do there. One of the challenges is that if you remember back to the hydrodynamic timescales, it goes as the size of the system. So, if I could make a nicely filled optical lattice that was 1 millimeter on a side, that'd be beautiful, because then I'd have the nice separation of time scales, so I could still see this physics. But with the typical kind of length scale you get for an optical lattice, the system would explode due to the hydrodynamic forces, and it would be very difficult to disentangle all these things. So there still might be very interesting things to do there, but that's one of the reasons why I haven't gone in that direction.
Eric?
So I have many questions, but I'll limit myself to two. One, it strikes me that as the cloud expands, the kinetic energy will go down faster than the nearest neighbor interaction energy. One question is, can you expand your way into stronger interactions? And the other question is, I know that I understand why the electrons and the ions should have very different temperatures, but in terms of them coming to equilibrium with each other, are we talking milliseconds, seconds, hours?
Many milliseconds due to the mass difference. Yeah, so that's important for the experiments. The question on, yes, you are actually absolutely right. As you adiabatically expand the system, the Coulomb coupling does actually increase. And so we've done those experiments, and that we've been able to show it going from the gammas of 2, we've gone up to about 5 by letting it expand. Unfortunately, that takes a long time, and you're also, I didn't mention this, but you need to keep those electrons warm, otherwise you get the recombination. So that's a heating source that's always heating the ions. So that's why we just can't keep going forever and ever expanding our way into strong coupling.
Okay, any question from upper level? Okay, if not, there is one question that online attendant asks. Okay, what is the electron-ion collision rate? Do you observe any enhanced momentum diffusion from excited state collisions?
Can you repeat the last part of it?
Okay. Do you observe any enhanced momentum diffusion from excited state collisions?
Okay. No, we don't see any changes to the diffusion through excited state collision. The electron to the ion collision rate is very, 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 very fast because the electrons are moving so quickly. But the electrons are so light that it leads to very little momentum, and that's why we have the many milliseconds of equilibration. The ions are essentially colliding all the time. That's really what strong coupling means, is that you're constantly in interaction with the particles around you. It actually can be difficult to rigorously define a collision rate.
Okay, it's the right time to move on to the next speaker. Okay, thank you to Tom.